Good day to all of you. Today we shall discuss on the topic cache memory and mapping functions. Our acknowledgement to author Carl Hamicher, who is the author of book with title Computer Organization 5th edition. So here in the figure we can see processor and main memory connected over the bus. So we use computer for processing the information. Computer is a digital device. So heart and brain of the computer is processor. It can process the given instructions. And these data and instructions permanently they will be stored in hard disk. But during execution it has to be loaded into main memory because processor directly contacts with only main memory but not secondary memory, that is hard disk. Hence during execution whatever program you want to be executed, during execution it must be loaded into main memory. So from main memory processor will access data and instructions and computes the execution. But part of the program or data is copied into cache memory, that is here on chip with processor. It may be outside the processor also. There are different kinds of cache. So these are the fastest memory elements. So processor, instead of accessing main memory, now it is made available in cache only. Hence it can very quickly access the needed data and instruction. So access time is reduced, execution time is reduced, hence speed of the computer will be increased. Okay, so cache is for increasing the speed of computer. It is treated as a part of a processor here. It is called as primary cache. But outside the processor IC, if any cache is made available, that is called as secondary cache. So whenever some data and instructions are copied from main memory into cache, they are retained there once executed, treating that they may be required in near future again. So if you consider the memory hierarchy here, we can see black part here, that is processor. It is having registers and part of cache on chip with processor, that is called as primary cache. And then we have secondary cache. Okay, that is the cache outside the processor. So next we have main memory, that is primary memory, and secondary memory, next hard disk, for example hard disk, right? So whole of the memory is not provided in single unit, but it is provided in multiple units as primary and secondary memories. So secondary memory here, for example hard disk, it is permanent storage device, non-volatile. Even if power is switched off, the data and instructions are retained. They are not erased. So we save our programs and data in hard disk. But during execution, the program is to be loaded in main memory. Hard disk is magnetic type. Main memory and cache are electronic memory. Okay. So this figure shows memory hierarchy, different levels of memory units. So to the processor, nearest one is register, it is the fastest. Next nearest is primary cache, but it is slower when compared to register. Next outside processor IC, what cache is available, that is called as secondary cache. Then main memory is little more slower than the cache. Okay, then the slowest is magnetic. So as we move away from processor here, registers, cache, in that primary cache, secondary cache, then main memory, and then secondary memory. So the speed goes on decreasing here. Cost also decreases. Hence more size of memory for the same cost can be made available. That is what is these three arrows are telling. So the first arrow increasing size, it is downward. So As we move from register to cache, main memory and then hard disk, size can be increased. But from hard disk, when we move to main memory, then secondary cache, primary cache and register, the speed is increased. Means cost also increases here, but size reduces. So as the speed is increased, the cost that we have to pay for the same size memory goes on increasing. Hence, for less costly memory, if you want, then we'll have to pay more, or reduced speed but with more memory capacity we can purchase. That is what is this figure is representing. So then cache memory, it's a very special high speed memory. It is small, costlier than main memory and disk. But when compared to registers, it is economical. Registers are costliest and fastest. So these cache memory store the copied content from main memory, right? So primary cache means cache which is available on chip with the processor. Next, secondary cache, which is the cache which is outside the processor IC, right? These cache memory are made up of SRAM integrated circuits, static random access memory integrated circuits. They are fastest but costliest one. Hence, in small size, cache can be provided. Because on chip with processors, space available is less, a very small amount of cache can be provided on chip with the processor. Remaining cache has to be outside the processor IC, and that is called as secondary cache. So here it is L2 level. On chip, that is primary cache, is L1 level. We have L3 also, which can improve the performance with L1 and L2 level of cache. Here only two levels are shown. Okay. Then main memory will be made up of dynamic random access memory ICs, which are less costly. Magnetic, that is hard disk or secondary memory, are made up of magnetic devices. So they are very very cheap. Size also can be provided more, but they are the slowest. So when we study cache, we must know cache mapping, right? Here in the figure, two figures are there. The one already we discussed just now, memory hierarchy, and one more is showing the connection between processor and main memory, and it is showing L1 level of cache. So anyway, cache makes execution faster. So effectiveness of cache mechanism depends on locality of reference. What is meant by locality of reference? So the property of programs it is, that is used in an advantageous manner by cache as to reduce access time and hence increase the speed of computer. There are two terms attached to locality of reference. Okay. Then temporal means at present what processor is executing an instruction, that may be executed again. Likely, it is likely that same instruction may be executed again in the near future. That is with time, repetition of execution of same instruction. That is temporal kind of locality of reference. Spatial means whenever an instruction from program is brought, in the nearby which other instructions are there, chances of executing that will be more. Hence, instead of fetching only one instruction from main memory into cache, a block of instructions or words must be fetched and copied into cache. Then number of access that the processor has to make with main memory will be reduced because everything is made available in cache. That is what is locality of reference, and one with respect to temporal, another with respect to spatial. This property of program cache mechanism uses. Then only it can reduce the access time and hence increase the speed of the computer. So temporal kind of locality of reference, spatial kind of locality of reference. This is what I just now explained. So recently executed instruction is likely to be executed again very soon. Hence it should be maintained in cache once brought until it is needed again. This is called as temporal locality of reference. Okay. Then instructions in close proximity in the neighborhood, that is, of recently executed instructions are also likely to be executed soon. Hence, while fetching an item from main memory to cache, instead of only one item, several items that reside in adjacent are copied from main memory to the cache. This is called as spatial locality of reference. The memory control circuit should make the advantage of locality of reference property of programs for best utilization of cache memory. Then we have mapping functions, that is cache mapping functions. Mapping means corresponding, means a part of program that is copied from main memory to cache so that it is executed by processor fast. Whenever processor requests for a word of data or instruction, it specifies the address in main memory. So where that data is available in cache, finding this, the technique, that is called as mapping function. So the correspondence between main memory and cache memory is called as mapping function. In another word, where to find a physically addressed word of data from processor into main memory, where it can be found in cache memory, and the technique of finding is called as mapping function. Memory hierarchy we have already discussed, and the same thing here. So what was there with the processor? Register, primary cache was shown. Anyway, next to registers we have cache memory, main memory, then secondary storage device, right? So in secondary storage device we have stored the program and data. In terms of pages, it is loaded from secondary storage device to main memory, that is called as virtual memory mapping. From main memory to cache, it is loaded in terms of blocks. Okay, from cache to registers, it is loaded in terms of, or it is copied in terms of words. Now the topic of discussion is the correspondence between main memory and cache. Means when a processor asks for a data, in which block it is in main memory, so that is available in which block of cache memory, because the processor will give physical address of the data in the main memory, which is in the main memory. That address data where it is available in the cache, the technique of finding, that is called as cache mapping. Okay, one term we have to remember here: between main memory and cache, the data transfer is in the form of blocks. Blocks means group of words. Whenever a processor requests for a word specifying its physical address in main memory, not just one word but a group of words called block is copied from main memory into cache. So block means group of words in main memory. So that also can be called as block in cache, group of words in cache. Another name is line. So line in cache means it's a block in cache. So block in main memory means group of words, line in cache means group of words, Whenever a block is copied from main memory into the line of cache, so it perfectly fits. Means the block size in main memory and line size in cache both will be same. If block size is 8 words, then line size also will be 8 words. When asked for one word in main memory, a block means 8 words when transferred or copied from main memory block to cache line. Because line size is also of 8 words, it can be perfectly copied. So with this understanding, let us move on to next. So here important note, what was the bigger figure in that, starting from register, cache, main memory till secondary storage device we had seen. Now we are focusing on the correspondence between only main memory and cache in terms of blocks, where a block of data from main memory can be found in a line of cache, that is cache mapping. So the main memory gets divided into multiple partitions of equal size known as frames or blocks. So another name for blocks in main memory, that is called as frame also. The cache memory is actually divided into various partitions of the same size as that of blocks. Here in cache they are known as lines. The main memory block is copied simply to the cache during the process of cache mapping, and it doesn't look like for the user as though it is coming from main memory only, but it will be coming from cache to processor because it will have already been copied from main memory to cache. So in the technique of finding the block of memory where it is copied in cache, in which line, a block of main memory is copied into which line of cache. So technique of finding, that is mapping function. There are three different kinds of cache mapping functions. The first one direct mapping, second one associative mapping, third one set-associative mapping. Here just the figures are shown that cache comes between processor and main memory. Be either primary cache or secondary cache or simply cache. Anyway, this faster memory element comes between processor and main memory. Okay. So whenever processor asks for a word, it is searched in cache. It will have given the word address in main memory. Because it is copied into cache, then it is given to processor. Hence that word is first searched in cache. If that word is found there, then it is called as hit. Otherwise miss. Okay. If it is miss, it should be copied from main memory to cache, and at the same time it is supplied to processor also. First it is supplied to processor and copied and kept. Second time when it asks for the same instruction or data, so it is searched in cache. If it is available, it is a hit. Otherwise miss. Right? So like this, if many instructions when copied, the cache may get full. When a new data is asked from the processor to memory, some old data is to be removed from cache. Then which line of data in cache has to be removed? For that, various replacement algorithms are there. Following that, the memory controller unit will remove a line of data from cache as to accommodate newly brought word from memory into cache. Okay. We'll have to see the first one, that is direct mapping. So what were the three mapping functions? Just now what we saw here, direct mapping, associative mapping and set-associative mapping. So first we shall take what is direct mapping. The easiest technique in cache mapping is direct mapping, but it has some disadvantage also, right? If program continuously access multiple blocks of data that share the same line in a direct mapping cache, the line will be rewritten often. This results in lot of misses movement. So direct mapping has a lower hit rate than other cache mapping models, because what this is telling, when cache size it is smaller, some lines are provided in cache where block of data from main memory can be copied. Okay, but whenever a block is copied, particularly in which line it is to be copied is calculated, and in that line of cache only block of that main memory is copied. Though other lines are free, they cannot be used. And if multiple blocks are mapped to same line in the cache multiple times, it has to be rewritten. So that is the disadvantage. Rewritten means it's a miss, the data is not available, hence it is to be copied from main memory into the same line. This new data is mapped to the same line, then old data has to be erased and new data has to be copied. So this is rewriting because of not availability, that was miss. So hit means what processor requests that word is available in cache. If it is not available, that is a miss. In case of miss, it should be overwritten with new data from main memory to cache line, main memory block to cache line. Okay, so though direct mapping is simplest one, it has this disadvantage of many times rewriting because of many misses. Short terms already we came to know a cache is organized into lines, right? Each line is only large enough to store one block of data, that is from main memory, and the tag to identify where the data came from. So that is, whenever a block of data from main memory, it is copied to a line in cache. So from where it is copied from main memory to indicate, tag bits are also stored in the cache. When a user requests a piece of data, computer first scans cache to see if information is there. If it is, the information is returned to the user. This is known as cache hit. This is exactly we already discussed, which is quicker than retrieving data from original location. The percentage of requests that results in cache hits is called as hit ratio. If the data the user requested is not in the cache, the computer will find it in the main memory. Copy of the data will be deposited into the cache so that it can be found quickly the next time the user requests. It is increasing the hit rate. All of this happens behind the scenes. The user doesn't know if the data is received from cache or main memory. This figure is for understanding direct mapping. So main memory with green color, what is shown here, then cache with yellow color, and physical address in terms of here tag bits, line number, block or line offset, right? What is this? Whenever a processor requests for a word in main memory, it sends the physical address. The division of physical address in direct mapping, it is in terms of three elements. The first element is tag, second is line number, third one is offset. Middle figure for cache, one line, that is line 0. Next memory partition is line 1. What are these? These are the spaces in which groups of words can be copied. Next in main memory, block 0, block 1. Group of words, here it is called as block. In cache it is line. Say block 0 if copied to line 0. If block 0 is having the capacity of storing 8 words. Line 0 also must be having the capacity of storing 8 words because block is copied into line. The size of both will be equal. So whenever copied, from where it is brought in main memory to cache. So to identify, tag bits are also stored for every line of data. Say one block from main memory is copied into one line of cache, from where in the main memory it is brought to cache. To identify that or to indicate that, tag bits are stored. That is what is the tag bits in physical address division here. It indicates from which part of main memory it is brought to the line of cache. Line number indicates which line in the cache, right? Then offset indicates in that line which word. Say group of 8 words are stored. Is it 0th word, 1 word, 2nd word, 3rd word, like that, last word, 7th word. So the words stored in that line, group of words, they are numbered from 0 to 7. Hence it can indicate 8 words are stored. So exactly which word? First word means 0 word. Its address is 0 in that line. Then 1, 2. So that is called as offset. If 2, it is indicated in binary. What is 2 in binary? 1, 0. Suppose 8 words are there, minimum 3 bits are required to represent which word. So last word means, 8th word means it is address is 7. Its offset is 7, 1, 1, 1. That is stored in offset part. Line number. If there are 16 lines, to indicate which line 4 bits are required. So last line means 1, 1, 1, 1. That will be stored in line number part of this division, physical address division. Then tag means how many cache block. Cache is small, say of 16 words. Then if main memory is of 64 words, then how many cache sized memory partitions can be done in main memory? Here 16, there 64. Hence 16 fours are 64. So 4 times the main memory is bigger than cache. Hence cache type 4 partitions are there in main memory. Then first partition is 0, 0, second one is 0, 1, third one is 1, 0, the last one is 1, 1. This is tag bit. If 4 partitions of cache size in main memory can be done, that is to identify that what bits are reserved, they are called as tag bits. This is how physical address division is done in direct mapping. Okay. So this figure, our acknowledgement to author Karl Hamacher of the textbook with title Computer Organization and 5th edition, from where I have taken our sincere thanks and acknowledgement to author Karl Hamacher. What is shown here, whatever so far with some colored figure we discussed, the same thing. The bigger one main memory, the middle one smaller, that is cache memory, and the left side what is shown, that is the division of physical address given by the processor. Physical address of the word that it requests, where it is in main memory, that physical address given. How it is divided in direct mapping? It is divided into 3 parts: tag bits, block, number indicating bits, then word means offset, which word in that. So here a calculation. So block J of main memory is found in block J modulo 128 of the cache. So what they are telling with this, how to do calculations or correspondence in this technique, how it is done. So here the main memory size, here you can see the last block is 4095, the first block is 0. 0 to 4095 means 4096 blocks are there, that is 4K. Anyway, 4096 blocks are there. Here in cache 128 blocks. So here you can see block 0 and block 127, 128 blocks are there. So where block of main memory can be found in block of cache. Instead of line, they have used the word block, same word in cache also. Suppose block 127 in main memory, if I take 127, right? So block 127 in main memory, how many blocks are there in cache? 128. Block 127, if copied, if any word is requested from processor belonging to block 127, then block 127 is copied into block 0, that is 127. Okay, is that clear? 127 modulo 128, that is 127 only. Next, suppose block 0 of main memory is copied, 0 modulo 128, that is 0 only. So block 0 of main memory is copied into block 0 of cache. Block 1 of main memory is copied only in block 1 of cache. Like that, block 127 is copied into block 127 of cache. Block 127 of main memory is copied into block 127 of cache, right? Next, if you think block 128 of main memory, so there 128 modulo 128, right? So that is 0, correct? So then if 128, that block 128 is copied into cache, it is copied in block 0 only. The old content will be erased and new content is written. 129 is copied in block 1, 130 in block 2, like this. Earlier it was from the first partition, cache size partition in main memory. Now second partition. Like this, how many cache size partitions can be made, from which partition it is coming, that is indicated by the tag bits in cache. So that is what is given here. Thus main memory block 0, 128, 256, they are all found in block 0 only, because 0 modulo 128 is 0, 128 modulo 128 is 0, 256 modulo 128 is 0. What we are trying to express is, suppose block 128 of main memory is copied, where it should be copied? So cache size is also 128, that is why 128 modulo cache size 128. 256 in main memory, that block modulo cache size 128. So that modulo, that result is coming out to be 0. Hence all are mapped to block 0 in cache, right? 1 block 1, 129, 257 onwards. If you take modulo with 128, it comes out to be 1. Hence these are mapped to block 1 in the cache. So that is what is correspondence. Where to see main memory block, in which block of cache it has to be seen, right? We'll take up one example for better understanding. A small example. In this example, number of cache lines is 16. Next, main memory size is 512 words. This is total size they are telling. Block size is 4 words. In each block, how many words it can accommodate? 4 words. The number of cache lines, how many are there? 16, means 16 blocks. Then total words stored in cache are 64 words. Like this, in main memory totally how many words are there? 512. Then 4 words if we keep in one block, how many blocks we can make in main memory? So 512 by 4, right? Like this we can do some calculation, but the question is what are the number of bits in tag. It is their question. As a part of solution, the diagram is given here. So how many blocks are there here? So 0 to 127. Why 127? So totally 128. 128 into 4, 512. Total number of words main memory that can accommodate 512 they have given. See here, the main memory size 512. That is why, and block size also 4 words. So with this data, in 4 words in each block in main memory, starting from block 0, how many we can have? 512 divided by 4, that is 128, hence 0 to 127. Next, what again another data they have given? Number of cache lines or blocks is 16. So 16. So 0 to 15. Block size and line size will be same, 4 words in each. Right? So what are the number of tag bits? It is their question. So here what we can see, the cache size 16 into 4, 64 words or bytes you can see here. Number of lines or cache blocks are 16 and 4 words in each line. Hence to represent lines means blocks, how many number of blocks are in cache? They are 16. So to indicate 16, 4 bits are required. So here the line number, that is 4 bits. Okay. So that can indicate 16 lines are there in cache. In each 4 words are there. So to indicate one among the 4 words, 2 bits are required. Right. So here 2 bits are required. So 2 plus 4, how many? Totally 6 are over. But total number of bits depends on physical address. So totally how many words are there? 512 words are there in main memory. To indicate the address of 512 words, how many bits are required? To indicate 512, 9 bits are required. What I have written here? Okay. Here 9 bits are required. So 9 minus 4 minus 2 is 3. Hence the answer we will get it as 3. So the answer for this question, the number of bits in tag is 3 bits. With 3 bits, how many we can represent? 8. Then cache sized partition in main memory, how many are possible? 8. So from 0 to 7. 0 means 0, 0, 0. With 3 bits we'll write. First partition in main memory. There, then second partition 0, 0, 1. The last partition 1, 1, 1. So whenever a block is copied from main memory to cache block, then from which part of the main memory? Means is it going to belong to the partition 0, 0, 0 or 1, 1, 1 or 0, 1, 0? That is tag. Along with tag bits only, that block is copied into, as per calculation, calculated line of cache. That is what is the solution of problem 1. Right? Let us take up another problem, example 2. In this, consider a direct mapped cache of size 32 KB, means 32 kilo. 1 K means 2 raised to 10. 32 means 2 raised to 5. 32K means 2 raised to 5 into 2 raised to 10 bytes. What is the number of blocks in cache? So 32 KB divided by 32, 1 KB. So 1 K blocks will be there. 1 K means 2 raised to 10. 10 bits are required to represent how many blocks are in cache. That is the middle part in the physical address division, that is line number. Right? In each 32 bits means to represent any one, 5 bits are required. So which part I am talking to here? This physical division. So what you can see, line number Here 32 KB divided by 32 is 1K. Number of lines or blocks are there in cache. 1K means 1024, that is 2 raised to 10, 10 bits. So 10 bits are taken to represent line number here. In each 32 words means 32 bytes mean to identify any one byte, 5 bits are required. 5 bits are reserved for word offset. 10 bits for line number, then 5 bits for word offset. Right? This much we can do till here. The number of bits needed for cache indexing and the number of tag bits are respectively. Already we came to know that 10 bits are required for line number. Means cache indexing means where to find in the cache. Means in which line, which word or byte here. That already 10. So 1 or 2. 3 and 4 option cannot be correct. So next one, tag bits we'll have to find. Already we found in our discussion line number 10 bits, word offset 5 bits. How many tag bits? This depends on main memory size. So exactly this is what I discussed with respect to previous problem. Line number 10 bits, offset 5 bits. Total, if we know, if you minus these two, then we'll get how many tag bits. Okay. So solution, cache memory size 32 KB, block size or frame 32 bytes. The number of bits in physical address they are telling 32 bits. Here only we can know 32 minus 10, 22. 22 minus 5, that will be 17. So let us see whether here the same whatever we discussed. Number of bits in block offset, that is 5. Already we had calculated 10 for line number. Block offset is 5. Right? So after that, for the same problem here, so line number 10 bits, that is okay. So 10 plus 5, total number 32, because they have given the total number of bits in physical address is 32. 32 minus these two we will get. So 32 minus 10 minus 5 will get 17 bits. 17 bits are there for tag. So the answer option A is correct. Here in the option A, 10 and 17. For cache indexing, the line number for representing 10 bits, and for tag bits it is 17. Hence option A is correct. So that was the discussion so far. What was the topic discussed so far? Cache memory and mapping functions. There are 3 mapping functions. In this we have covered one mapping function along with its theory and some of the example solving. The remaining we shall cover in the next video. Okay. I hope all of you understood. Thank you.